Hall-White model. The Hall-White model is as follows. Here, Hall-White model dRt equals theta t minus gamma RT dt plus sigma gg. It looks similar to Hall model. The only difference is this part. So if we don't have this part, if this gamma star is 0, this gamma star is 0, then if gamma star is 0, then it becomes Hall model. Okay? So similar to Hall model, we want to calibrate this one. We estimate this one and this one. We estimate on historical data, and we calibrate. Then question is, it is very similar to Hall model, but why we use a Hall-White model? Well, think about it. When interest rate is very high, then it is big negative, so future interest rate go down. On the other hand, when interest rate is low, then it is a small negative, so well, this one dominates, so future interest go up, right? So if by including this term over here, we can generate that there is like mean reverting, interest rate mean reverting. We can model that interest rate is mean reverting. And indeed, interest rate is mean reverting. If interest rate, for example, if interest rate is too high, then central bank will lower the interest rate. On the other hand, interest rate is too low, then maybe central bank will increase interest rate. So in data, interest rate follows a mean reverting pattern. In Hall-White model, by introducing this gamma star term, we can make interest rate mean reverting. There is some equilibrium level, some equilibrium or long-term level. And when interest rate deviate from long-term level, then the interest rate tends to go back. There's a property that this interest will go back to the long-run level. Of course, there is continuous shock of this one from this Brownian motion, but still, because of this one, the interest rate has some mean reverting pattern. So this is a nice property of Hall-White model. And from Hall-White model, now our code is same. From Hall-White model, we generate bond price or other prices, and we match theoretical price and empirical price or prices we can observe from data. Then we can calibrate this one. Calibrate. Okay. Then our first step. So given this Hall-White model, how we can find the bond price? Well, that is very similar to Hall model. First, very similar to Hall-White model. No, very similar to Hall model. We first conjecture that bond price is exponential of some a minus br, and we impose zr big T is 1 because it's face value. In differential equation setting, this is often called the boundary condition. In mathematically, it is called boundary condition. Boundary condition. And this boundary condition is economically intuitive because price of the bond at maturity should be same to face value. Then we can set up the investment process for zero coupon bond. Like this is the buy investment, and it is cost of buying it, like opportunity cost, so it is investment process. It is sometimes called zero cost portfolio because there is no cost to produce this process. You can simply borrow money from the bank and invest in Z. And now about this DZ part, you can apply Taylor series expansion. Then this DZ part is the TDT and ZRDR plus ZRR over 2 and DR square. And our cost part, RZ dt, this is same to this one. So we have this one. Now we have to find these ones, right? ZT, CR square, and dr square is simply dr square is, of course, square of this term, and this term doesn't matter, so dr square, we know dr square is simply, this term only matters, so sigma square dt, sigma square dt. Okay, so let's calculate what is ZT, ZR, ZRR. First, ZT is basically same to previous. ZT is AT, BT, RZ, and ZR is minus BZ, and ZRR, V square Z, and DR square is sigma square DT, and this one EZRT is theta T, gamma square, gamma star RT dt. Here we don't have a sigma ZZ because expectancy Z is 0. So we can plug this one. To plug them and put this, because we are in the risk neutral world, put E star dz minus RZ, this is 0. We have this one. This is the same to previous, only this part is different. In the Hyoung-Goo model, we don't have this part, we have only this one. But now, because expectation of R, because of we have this part, we have this part, right? So we have this one, ZT. And both sides, we can delete this part, we can divide it as this one, so we have this one. And we have R over here, we have R over here, right? R over here, and we have R over here, right? So put R term together and other term together, then we have this one. So we have original partial differential equation, and we divide that into two ordinary differential equation. So this one should hold for all R, for all R. To make this one hold for all R, we have to make 0, and we have to make it 0. Let's make it 0. So basically, we have two ordinary differential equations. We want to make one 0 and we want to use one 0. And we have boundary conditions. A, T, T equal B, T, T is 0. This one is from this boundary condition, right? This one implies that, A, T, right? Here I ignore this big T term. B, big T, 0, right? From this one, because it is 1, so this one should be 0. So we have this one. Then our strategy is same. Well, in this part there is no A term, so we solve this one first, and then we solve this one by plugging the first solution of V into here, and we can calculate A. That's our strategy. So we want to solve this one first. Well, in the previous case, in the case of Hyoung-Goo model, we don't have this one. In Hyoung-Goo model, we don't have this one. But now we have this term. No, we only have this term. But now in the whole white model, now we have this term. Then how we can solve this one? Well, let's write this. BT is, BT is basically shorthand notation of dB dt, right? So we put this one over here. Instead, we shorten the rule right here. So 1 plus dB over dt minus gamma star b equals 0. Now, let's decompose dB term and dt term. Let's multiply dt term each side. Then we have dB. We multiply dt term each side. Then it is dt by multiply dt term each side, then it is dB, because basically it's the ratio between dt, very small change of dt, and very small change of dB because of dt. So gamma square b dt equal 0, right? By multiply dt. So we have dt term together, and put left hand side, we have dt term over here, over here. So big dv is minus 1 minus gamma b dt, right? And we divide each side with 1 minus gamma b, then we have this one. Then how we can solve this one? Well, we have want to simplify first this one, okay? And in order to get simplify this one, we use this idea. You know, this d ln x dx is 1 over x, right? So by using chain law, applying chain law over here, so d ln 1 minus gamma p, and db is 1 over 1 minus gamma star b, and we have this one, we have to use chain rule, so b, so we have a minus gamma term over here, so minus gamma star. So this looks like this one. And this one looks exactly very similar to this one. To make this one and this one same, all we have to do is we multiply 1 over gamma star each side. 1 over gamma star each side. 1 over gamma star each side. Then they cancels out. And this one is exactly same to this one, right? So we multiply dv each side, then you can dv actually. So then this part, right? This part is exactly same to this part, right? So basically, so this part is basically 1 over gamma d ln 1 minus gamma b, right? So like this one, minus 1 over 1 minus gamma b, dv is 1 over gamma star d ln 1 minus gamma b, right? Now, because we have this term, so we want to integrate both sides, but this term is equal to this one. So we want to integrate both sides from here to here, and then if we integrate this one from big T and small t, it's big T minus small t. And for this one, E integrates from big T and small t, then you have this one. You have minus over here because of BT, because we know BT is 0. So it is basically minus 1 over gamma and B small t, because the BT term goes away. It is 0, so it is log of 1, so it is 0, so we have minus 1 with this part. So, well, you can, from this one, now we can solve B. Right? We can first multiply minus gamma star each side, and then we take expectation, and then we put 1 over here, and then we divide each side with minus gamma, then B looks like this one. So we could compute B. Alright? By the way, when we solve this one, when we solve B, this one, what we did is we separate B and T each side, and then we solve it. So solving this kind of ordinary differential equation, in this way is called separation of variables. Separation. We separated B and T, right? Separation of variable B and T, separation of variables. So, in order to solve this ordinary differential equation, we separate BT, and by using this separation of variable technique, we can solve B. So this is solution B. Now, because we calculated B, and then we can plug this B into the equation for A, and we can calculate A, right? So AT looks like this one. Here, this equation is from this one, right? AT is minus plus BT. You can put this on each side, then we have the same. Right, AT is B theta minus sigma square B square over 2, and we know B, right? We know B. So here, we plug this one over here, and for this one, we integrate from big T, small t. But because ATT is 0, right? then we can only consider a small t, big T, right? So we have minus sign over here. So we have equation for A, right? Here B is, we already calculated this B. So now we get A and B. Now from her white interest rate process, we computed the bond price, zero coupon bond price. And by comparing this zero coupon bond price with the real zero coupon bond price, we can observe in the data. We can now match the model. We can calibrate the model. To calibrate, and we can find this theta. Then we are done, right? But instead of matching the bond prices, here also, if we match forward rate data, actually we can find theta more conveniently.